So next, to understand why or how the fundamental group of x comma x is a subgroup of the automorphisms, homeomorphisms of the universal covering space. Okay. So why is the fundamental group of the base space, why can it be identified naturally as a subgroup of automorphisms of the universal covering, automorphisms which are of course homeomorphisms, okay, self-homeomorphisms. Okay. So so for this one has to go through a small construction. So so we will do the following thing. Suppose x tilde to x p is a covering space. You just take any other covering space of x, okay, fix the point, in fact so fix a point, x tilde belonging to capital X tilde with p of x tilde. Let me call this as p tilde because I have used p already. Okay, p is supposed to be our covering map from the universal covering to x. Okay, so so let x tilde from p tilde to x be covering space, and you fix a point in small x tilde and capital X tilde, okay, which lies over x. Okay, so so the situation is like this. So here is x sub univ. I fixed in x sub univ. Of course I am going to take the natural point, namely the constant path at x, which lies above x, small x in capital X. Okay, and then I am going to take another, so there is another covering space x tilde given to me along with the covering map p tilde. So this map is p, okay, and I have a point here, namely small x tilde, which is also lying over x, okay, under the map p tilde, right. Now what I am going to do is that I claim that this much of data is enough to define a map from x from this universal covering to that covering, such that this map itself becomes a covering. Okay, so so I am going to do the following thing. Okay, so I am going to do the following thing. Take any point of x sub univ, okay, say alpha. Okay, now well this alpha well is going to correspond to me to a path here, alpha starting at x. Okay, and I have so you know and of course for this alpha there is this very natural alpha tilde that we constructed, which is given by the shrinking homotopy. That is the path that lifts alpha, okay, to the universal covering. Right. What I am going to do is, now since I have a path here and since this is a covering, okay, there is a lift of this, there is a unique lift of this to a path starting at x tilde. Okay, so what I am going to get is I am going to get a path here. Let me call this as alpha hat, okay. So this alpha hat is unique lift of alpha, okay, to x tilde starting at x, okay, and it has an endpoint, and I am going to define a map which will send this alpha to this point, okay. So what I am going to do is, this is my map, so this is my map phi, and this map depends on this x tilde, okay, that I have fixed there, right. So let me write that down. So define the map phi sub x tilde from x sub unit to x tilde, okay, by sending alpha to alpha hat of 1, where alpha hat is the unique lift of alpha to x tilde starting at small x tilde, okay. So this is my map, right. Now the point is that this map is well defined, this map is well defined because if I change alpha by something that is homotopic to alpha, so then that means I will change, if alpha is also homotopic to beta, then I'll have a beta here, okay, which is fixed endpoint homotopic to alpha, and then you know beta will also lift here, okay, but then the covering homotopy, theorem says that fixed endpoint homotopies can be lifted to fixed endpoint homotopies, so the lift of beta hat of beta will also have the same endpoint as the lift of alpha hat. So this map is well defined even if you change alpha up to homotopy, fixed endpoint homotopy, okay. So this is a well defined map, okay. Now it's somewhat of an exercise, basically using the fact that these are local homeomorphisms and they are covering maps. A little exercise will tell you that this itself is a covering map, okay. So let me write that a little work exercise shows phi sub x tilde is itself a covering map, okay. So this is some work that needs to be done, all right. You can verify that for yourselves, all right, and what I would like to say is that in some sense this whole thing is gives what is called as a universal property of the universal cover, okay. So so let me say something more, and it actually lifts P. So you see what is happening is I have x sub uni, okay, and I have this map P to x, okay, then I have x tilde P tilde, this is your covering given to you, and then there is this point Cx here which goes under P to x, okay. There is this point small x tilde here which goes also to the same x, okay, and what happens is that I am able to define this phi sub x tilde, and this diagram commutes. So this phi sub x tilde is a lifting of P, okay, and it has a property that it sends Cx to x tilde, okay. If I start with the if for alpha I took the constant map at x, then it will go down just to the constant it will just go what I get here is the constant path at x, and its lift will be unique lift will be just the constant path at x tilde. So you know constant path at x will go to x tilde, so this is what happens under this map, okay. So let me write that also. Note that phi x tilde is the unique lift of P to x tilde taking Cx to x tilde, okay, because you know a covering map you know the local homeomorphism has this uniqueness of lifting property. So if you have two maps if you have any lifting that agree at a point, then they will agree everywhere. So this lifting is completely controlled by the fact that this Cx this point goes to x tilde, so it is completely determined by this x tilde, okay. Now in addition, suppose so this is the so this is what is called the universal property of the covering. So what it does is the universal cover, you give me any other cover, okay, the universal covering space is also a covering space for any other covering space. This is also a covering map, okay, this is the so called universal property, that is the reason why it is called universal, okay. So this gives the universal property for the universal cover. So in fact I should not put this in quotes, I should rather put this in quotes, okay, x unit, which says x unit is also the universal covering is also let me say first it's also a covering of any covering x tilde of x, okay. This is the universal property of the universal covering, okay. Now what I am going to do is I am going to say the following. I am going to say that suppose in this whole construction that x tilde were also simply connected, suppose x tilde were also simply connected, then you can define an inverse map, okay, and that will be continuous and that will give you a homeomorphism of this with that, okay, and that gives you the uniqueness of the universal covering, okay. So let me state that. So that also essentially uses only the unique path lifting property, okay. So let me write that down. Suppose in addition that x tilde were simply connected, then we can define an inverse to phi x tilde and check it is continuous, okay. So you see essentially the game I played to define this map phi sub x tilde, the same game I can play to define a map in this direction which will be an inverse, namely what is that map. See from x So here is x tilde, and so it's something like this. So I'll need to draw a diagram again. So let me again draw a diagram. So here is x tilde, and here is p tilde. This is x, okay, and this is the universal covering x sub univ, okay, and what I fixed here is the point Cx, which is lying over the point x under the map P, and I have fixed a point there, namely x small x tilde, which is again lying over the point x under the map P tilde. Okay. Now what I am going to do is I am going to define psi sub Cx, okay, that is a map from here to here, and the way I do it is as follows: give me a point y tilde here, give me a point y tilde here. What I will do is, because x tilde is arcwise connected, I will simply choose a path. Let me call this as I will choose a path here, okay, from x tilde to y tilde, right, and I push that path down, okay, I get a path here. If I call this path as beta, okay, then this path is just the unique lift of beta starting at x tilde. So this is beta hat, all right, and now what I will do is I will also take the unique lift of this beta to x univ. So what I am going to get is I am going to get this path here, which you all know is beta tilde, that is there, and I am going to get an endpoint, okay, and this is a map. So this map is going to send y tilde to to this point, okay. So psi sub Cx is going to send y tilde to beta tilde of 1, okay, and you see so you see this point, which is beta tilde of 1, that lies over beta of 1, okay, and of course y also lies over beta of 1, okay. So this is also true, y also lies over beta of 1, okay, and if I, instead of beta hat, if I had chosen something else, which is another path from x tilde to y tilde, small x tilde to small y tilde, it is anyway going to be homotopic to beta hat, because x tilde is simply connected, and therefore its images here are going to be homotopic, and therefore the lifts here are also going to be homotopic. So this endpoint is going to be uniquely determined. So the simply connectedness is just used to tell me that I can define this map properly, okay. Now again a little bit of exercise will tell you that this map is continuous, okay, and it is an inverse to phi sub x tilde, and therefore phi sub x tilde will turn out to be a homeomorphism. So what it will tell you is, if x tilde to x is a covering space with x tilde simply connected, then that has to be homeomorphic to the universal covering space, okay. So this gives you the statement that any covering of x with the property that the covering space is simply connected has to be isomorphic to this covering, and it is not just a homeomorphism of these two spaces alone, it is a homeomorphism that respects the projections. So it's a so it's an isomorphism of covering spaces, okay. So it's an isomorphism from here to here, which this followed by this is this projection, and similarly phi sub x tilde going in this direction followed by this is this projection, okay. So so can check phi sub x tilde is a homeomorphism with inverse psi sub Cx, okay, and So let me repeat that this gives you the fact that any two covering spaces of X with which are simply connected are homeomorphic in a way that respects the covering projections, okay, and this is the so called uniqueness of the universal covering of a space, okay. Alright, so we have also got the uniqueness of the universal covering. Now I need to go on and tell you why the fundamental group below can be recognized as a subgroup of homeomorphisms of the covering, universal covering, okay. So so let me see whether I have written that down properly. So let me write one more line, any two covering spaces for X which are simply connected are homeomorphic in a way that respects the covering projections. So this is what you get, and this is the so called uniqueness of the universal covering. So this is the uniqueness of the universal covering. What it tells you is that you can get a homeomorphism, and the homeomorphism is unique if you fix a point in one and a point in the other, okay. So we say it's unique up to a unique isomorphism, okay. So if you want, you can find many. If you have two simply connected covers of the same space, you can get many homeomorphisms, but if you want to fix the homeomorphism, you have to fix a point here and its image there, then you have fixed it, okay. Fine. Now what I need to do is I need to tell you that the fundamental group of X, the fundamental group below, sits as a subgroup of automorphisms of the universal covering. So I have to identify a certain subgroup of automorphisms of the universal covering, and these are the so called deck transformations. So let me define the deck transformation group. Of a covering so what is this? So it is defined like this, the deck. So the notation that I am using is the following: deck x tilde x p is the set of all phi from x tilde to x tilde such that phi is a homeomorphism and phi respects the projection, namely first apply phi, then apply p, you get back p, okay. So basically the diagram is like this. So you can see these are of course homeomorphisms from x tilde to itself. So this is certainly a subgroup of the homeomorphisms from x tilde to x tilde, okay, which is just automorphisms of x tilde. The automorphisms of x tilde as a topological space, okay, the self homeomorphisms from x tilde to x tilde. This is a certain subgroup, okay. What is this subgroup? These are those which behave well with respect to the projection, and this actually means that these automorphisms they act on x tilde in the fiber direction, okay. So so the condition, so let me write that down. The condition P circle phi is equal to P says that elements of the deck transformation group act along the fibers of P. Namely, you see P circle phi of say a point y is equal to P of y. This actually means that phi of y lies in P inverse of y, P inverse of P of y. Okay, so you can imagine what's happening. So basically, so this is your x and this is your so of course I've used P tilde everywhere, so I should be careful about P tilde. So it should have been P tilde here because I've reserved P for the map that we have constructed. So let me change it everywhere to P tilde. So the situation is like this: you give me a point and you give me a admissible neighborhood. The inverse image under P tilde will be several several neighborhoods which are homeomorphically mapped by P tilde onto this, and what this deck transformation will do will essentially it will move these so called decks. Okay, you can think of them as various decks of a ship if you want, okay, or floors of a building, okay, and the action of each of these deck transformations is going to be only in the vertical direction. Okay, now you can guess what I am going to do. I am just going to show that the fundamental group I am just going to show that the fundamental group of X, capital X based at small x, is canonically identifiable with this, okay, and that finishes it. Okay, so let me do that. It's not very difficult to do. So define the map. So here is the map rho fundamental group X to fundamental group of capital X based at small x to the deck transformation group of so I am now going to take the universal cover that we constructed. I am going to define this map. Okay, so of course what I have said here is this is a deck transformation group of a general covering. Okay, I am now going to restrict to the case of the universal cover. Okay, so what is this map? So it's the following. So what I do is, suppose I start with a sigma. Okay, now a sigma here is a loop based at x. Okay, so my diagram is going to look like this. So here is small x and here is my sigma. Okay, and what I am supposed to do is I have to give you a map from x subunit into itself. Okay, so I start with a point alpha in x subunit, and I will tell you where it goes to under the image of this. So this will go to rho of sigma. I will define this as a deck transformation, and so this should be a map from x univ into itself. Okay, and what is this map? I will send alpha to sigma alpha. Okay, so you see, if I start with the point alpha, that's going to give me a path here. Okay, all right, and then it's going to end somewhere, and this point is going to be the point to which this alpha is going to be mapped. under this under the covering projection. So this is going to go to this, okay, and if I take sigma followed by alpha, that is also a path starting at x and ending at alpha of 1, so it's going to be another point here. So sigma alpha is also going to be here, okay, and therefore you see your map is like this. So it's a map that pushes along the fiber, okay. Now 2 or 3 things can be seen very quickly. Actually you can directly see that this map is bijective, okay. That's very easy to see rho of sigma is bijective, okay. That's quite easy to see. Why is that true? Because you see surjectivity, if I want to get hold of a beta, okay, then you know, I have to just send it to I have to just take sigma inverse beta, okay. This will go to sigma inverse beta, which is beta, okay. So this is surjectivity, and injectivity is obvious. If sigma alpha 1 is equal to sigma alpha 2, then alpha 1 and alpha 2 are homotopic, fixed endpoint, okay. So it's bijective, okay. There is nothing to, it's very easy to check that. But in fact the point is that this map is a map of this form. That's the whole point, and that's the reason why it's a homeomorphism, okay. Why is it a map of this form? It's so if I write it down, so let me rub this, let me draw another diagram. So you see what is happening is the following. I have my x here, okay, I have my universal covering here, okay, and I have again my universal covering here, okay, and these are of course again the covering projections, okay. What I am fixing here is of course over the point small x, the point I am fixing is Cx, okay. Notice that Cx goes to sigma, okay, and notice also that Cx and sigma are points over x. See, over x you have the point Cx, the constant path at x, the homotopy class, and sigma is a loop. So you see that is also a point here, okay, and both of them are lying above x, okay, and this multiplication by sigma acts on the fiber over x in the most natural way, okay. This is just multiplication by sigma on the left, okay, and in over every fiber that's what is happening, okay. So you see, choose this Cx, take x, and then you take here the point I fix the point sigma, okay, which is a point over x, okay, and I claim that if you take the corresponding map phi sub sigma, I claim that this map is literally the same as rho of sigma, okay. I claim that these two are the same. Of course, you know, you have to do some work to check that rho of sigma is a homeomorphism, okay. Check well, in fact, to check that rho of sigma is a homeomorphism, you can check that these two are equal and then use the fact that phi sub sigma is a homeomorphism, okay. So so let me write that down. Check rho of sigma is a homeomorphism, as follows by this claim. Okay, but see, why is this true? If I take a point alpha here, okay, where will this go to under phi sub sigma? Where will it go to? So, well, if you give me a point alpha, then this is a this represents the point the path alpha here. Okay, then I'll get this thing here, which is, see, this is the canonical lift of this alpha to the universal covering, which is given by the shrinking homotopy. Okay, and if I push it down, I get alpha. All right, now I take the lift of this starting at sigma. Okay, so I will get a lift alpha tilde, but now this time starting at sigma. Okay, this sigma is another point over x, another point in the fiber. So I get, and what is this endpoint? This endpoint is precisely rho of sigma. Okay, see, this endpoint will turn out to be actually sigma alpha. Okay, so you can see right, and why this endpoint will turn out to be sigma alpha is again because of the shrinking homotopy construction. Okay, therefore these two maps are the same, but if you already verified that this is a homeomorphism, then so is this. Okay, therefore, and of course the way I have defined it, it's going to respect the projection. So it's going to be a homeomorphism of the universal covering which respects the projection. So it's going to be a deck transformation. So this map certainly lands inside here. Okay, if I change sigma up to a homotopy, nothing is going to change. Okay, there is no problem. If I change sigma by a homotopy, you can check, it's obvious that nothing is going to change. So this is a well defined map. You can see that the identity element will go to the identity element here. Okay, because here is just multiplication on the left by sigma. So if sigma was the identity element, this will be just the identity map. So the identity element of this group goes to the identity element of that group, and you can easily verify that this rho is a group homomorphism because it's just left multiplication, literally. Okay, so this is a group homomorphism, and it's easy to check that this is both injective as well as surjective. Okay, so that can be checked very easily. So let me do that, and then we are done. So rho sub, so what was it? Rho of Cx is identity map on X sub univ, and rho of sigma 1 sigma 2, so I should say multiplication in the group here is rho sigma 1 composed with rho sigma 2. Okay, rho is surjective. How does one see that rho is surjective? It's very easy to see, because see, suppose you give me given a deck transformation, let's say phi, which is a deck transformation from X sub unit P to X. Okay, then you see this deck transformation will take the constant path at X to a certain path. Okay, so phi of Cx, okay, is going to be a point of X sub univ is such that you see rho of um, uh, um, okay, phi of Cx, okay, will be just phi, okay, because you see rho of rho of sigma is just phi sub sigma, okay. So rho of this for the left hand side is rho of this is just phi sub it is phi sub no, I didn't say this. These two are equal because they are both lifts of P and they both agree at Cx, okay, because both are lifts of P and both agree at Cx, that is why, okay. So rho is surjective and rho is injective, okay, namely if rho of sigma 1 is equal to rho of sigma 2, okay, then again the same reason, both of them will agree, I mean you apply these to Cx, okay, apply this to Cx, you will get evaluate at Cx, Cx will go under this to sigma 1 and Cx will go to sigma 2 homotopy class under this, so you will get injectivity, okay. So the upshot of this is that the fundamental group below is naturally a subgroup of automorphisms of the universal covering above, okay, and it is something that can be very explicitly seen, okay. So I think with this from the next lecture onwards I will move on, I will go back to Riemann surfaces and I will start deducing all the fundamental results that I told you by analyzing Mobius transformations.